Hi again, everybody. This is the last video of Unit 3, where we'll talk about the stability of organometallic compounds. When talking about the stability of organometallic compounds, it is important to distinguish between thermodynamic factors, we say they are thermodynamically stable or unstable, and kinetic factors, we say they are kinetically inert or labile. One must be quite clear with what type of stability is concerned. An ill-defined description of a compound as stable may refer to thermal stability or to resistance to chemical attack, especially oxidation and hydrolysis. Many organometallic compounds are easily oxidized in air, but can be stored perfectly under an inert atmosphere of nitrogen or argon. It is necessary to take into account not only thermodynamic factors, but also kinetics when seeing the stability of a compound. The heats of formation enthalpies, of organometallic compounds provide a measure of their thermodynamic stability. Notice that free energy values are not used, and that is because few standard entropy data are known for organometallics. In this figure, you've got the comparison of standard enthalpies of formation of methyl organometallics of the main groups. You also have the comparison in this table, where some are thermodynamically stable at room temperature with respect to the composition to their constituent elements, for example, tetramethylsilane or trimethylboron, which are squared in green. Others are unstable to such decomposition, that is, they are endothermic compounds. This is the case of dimethylmercury, trimethylthallium, or tetramethyl lead, which are squared in red. The low heats of formation of the methyls of the first short period elements are largely a consequence of the high binding energies of the elements in their standard states. And on the other hand, it has been found that these elements form the strongest metal-carbon bond. Remember that we have already seen that in main group organometallics, the metal-carbon bond strength decreases down the group. When compared to metal-nitrogen or metal-oxygen bonds, metal-carbon bonds should be considered weak. This bond weakness is reflected in the application of organometallic reagents in synthesis. It is not always easy to predict the thermal behavior of organometallic compounds based on standard formation enthalpies, as the composition often does not take place in the elements, but more complicated decomposition processes occur, for example, to afford hydrocarbons and metal. However, some endothermic compounds show considerable resistance to thermal decomposition because the activation energy of this process is high. That is, the composition can be kinetically controllable and can be multi-stage. As with organic compounds, all organometallic compounds are thermodynamically unstable to oxidation. The driving force provided by the great negative free energies of formation of metal oxide, carbon dioxide, and water. Some are also kinetically unstable even at low temperatures. However, there are large differences between them in terms of kinetic inertia. Almost all methyl derivatives of the elements of the main groups are rapidly attacked, although some are stable, such as those of group 14. Others, such as dimethyl zinc, trimethyl indium, trimethyl antimony, are spontaneously inflammable in air. Kinetic instability against oxidation may be associated with the presence of low-energy empty orbitals, for example, 5p in trimethylinium, or of a non-bonding pair of electrons, for example, in trimethyl antimonium. In contrast, the alkyl derivatives of the elements of group 14 do not possess any of these characteristics and behave like saturated compounds. Hydrolysis of an organometallic compound usually involves nucleophilic attack by water and is therefore facilitated by the presence of empty low-energy orbitals on the metal atom. Thus, in agreement with this, the organic derivatives of the elements of groups 1 and 2, alkaline and alkaline earth, and those of zinc, cadmium, aluminium, gallium, and indium are readily hydrolyzed. The rate of the reaction is dependent on the polarity of the metal-carbon bond. When this is high, as in trialkyl aluminium, rapid attack by water occurs, while trimethyl boron hydrolysis is not produced at room temperature, even though there is an empty 2p orbital in the boron atom. The alkyls and aryls of the elements of groups 14 and 15 are kinetically inert to hydrolysis by water because in these groups the metal is surrounded by a filled shell of 8 electrons, so that nucleophilic attack is not favored. Most neutral organic derivatives of transition elements are inert to hydrolysis. However, organolanthanides are extremely susceptible due to the polar character of the bonding, the larger size of the central atom, and the presence of many empty low-energy orbitals, all of which aid the coordination of the nucleophile. In your slides, you've got this table with these qualitative arguments that allow you to compare the different stability of some derivatives. Do not forget to have a thorough look at it. And do not forget, most transition metal organometallics are too sensitive to oxygen, and it is customary and often obligatory to handle them under an inert atmosphere of nitrogen or argon. Thank you very much for your attention.